We'll start off today by taking a look at electrical charges and the electrical force. First thing I kind of want to point out to you is as you compare electricity to gravity, think of charge as the equivalence of mass for the electric world. Probably by now you're aware that there's two charges, positive and negative. They are arbitrarily assigned. There's nothing special about the proton that makes it positive, and same thing with the electron, nothing unique that makes it negative. It's just their opposite signs, and we needed to give one positive, one negative. So it is arbitrarily done. Would our universe change in any way if we had reversed them? No. Both of them have a magnitude of charge of 1.6 times 10 to the negative 19th coulombs, the proton being positive, the electron being negative. Now, as for the unit C, coulombs, it just got the name because the guy who figured it out had the last name Coulomb. Protons are often considered to have a charge of positive 1e, and electrons negative 1e, where e is the electron charge. Now, as objects gain or lose charges, it's happening on the atomic level. Now, it's important to point out that the changes are caused by electrons moving. Protons do not move in the electric world. The addition or subtraction of a proton is actually a nuclear reaction. Let's take a look at our first example. Let's imagine you're walking barefoot on the carpet and you rub your feet on the carpet. This will build up a static charge on you, and that's why if you touch a doorknob, you'll sometimes get a shock. The friction between your feet and the carpet causes you to gain electrons and the carpet to lose electrons. So I want to point out, if something becomes positive in charge, it's because it lost electrons. And if something becomes negative in charge, it's because it gained electrons. So you gained 5.5 microcoulombs of electrons. So that's negative 5.5 microcoulombs. The Greek letter mu, pronounced micro for its prefix, means 10 to the negative 6. So negative 5.5 e negative 6, that's your charge in coulombs. Multiply it by 1 electron having 1.6 e negative 19 coulombs. Time to grab a calculator, and the results will be you gained a total of 3.44 e 13 electrons. So about 34 trillion electrons. Is that a lot? Not really. Would you notice the gain in mass? Absolutely not. Let's try another one. You have a sphere. It has 945 billion protons and 875 billion electrons. What's the charge? So I want to start by saying this. If you have one proton and one electron, the result is no charge. The two cancel out. Similarly, if you have 875 billion protons, which you do when you have 945 billion, and 875 billion electrons, the result is no charge. They cancel out. So you have an extra 70 billion protons in this problem. 70 billion, that's 7e10 protons. So the charge of one proton is 1.6 e negative 19 coulombs. The result is you would end up with a charge, calculator time, 7e10 times 1.6 e negative 19, 1.12 e negative 8 coulombs, or that would be 11.2 nanocoulombs. Either one would work. Some prefixes you should be familiar with: milli, micro, and nano. That's E negative 3, E negative 6, and E negative 9. The reason why is 1 coulomb of charge is an enormous amount of charge. So charges come in millis, micros, and nanos. Moving further, the electrical force is often called Coulomb's law because the guy who figured it out was named Coulomb. It is a natural force, just like gravity, therefore it does not require physical contact. Friction requires physical contact. Tension requires physical contact. If you're not touching the rope, there's no tension. Gravity is a natural force. You jump out of an airplane, the earth pulls you down, even though it doesn't touch you. Electrical force is just like gravity in that it's a natural force and therefore does not require physical contact. Now, the electric force is caused by an imbalance in electrical charges. Again, it's the electrons that are doing the moving, gains or losses of electrons. Charged objects are not attracted or repelled by neutral objects, but they can polarize them, causing attraction, and it would always be attraction and not repulsion. Also, unlike gravity, electrical forces can attract and repel. And you probably know from middle school, two positives or two negatives would repel each other. Opposite charges, like a positive and negative, would attract. You see here, F equals the absolute value of K, Q1, Q2 over R squared. The absolute value is placed there because we're not going to be concerning ourselves with the sign of the electrical charge, since for forces, negative means direction and it doesn't mean strength. You'll notice this equation looks very similar to the one in gravity. We just replaced the G with a K and the masses with a charge. F is the electrical force measured in newtons per usual. K is 9 times 10 to the ninth. If you recall, G was 6.67 times 10 to the negative 11th. That means K is significantly larger compared to G. The electrical force is significantly stronger than the gravitational force. Q1 and Q2 are the charges measured in coulombs, and R is the separation measured in meters. So let's put it to practice. Let's take a positive 5.5 microcoulomb charge, 5.5 microcoulombs, and 35 centimeters away, we have a negative 2.6 microcoulomb charge. What's the strength of the force? I want to point out by saying that the force will be attracting. It will be equal in magnitude but opposite in direction by Newton's third law. To solve for that magnitude, F equals K Q1 Q2 over R squared. So that's 9E9. Q1, 5.5 E negative 6. Q2 is 2.6 E negative 6. You notice I don't care about the negative. And then the 35 centimeters, make sure you convert that to meters. So that's a 0.35 squared. If you're successful, you'll get 1.05 newtons. That means, based on this diagram, my positive charge, which is here, has a force of 1.05 newtons to the right, and my negative charge here has a force of 1.05 newtons to the left. Going to our last example of the day. A pair of charges experiences a force of 64 newtons. The distance between them is doubled. What's the new force? Or instead, if the distance was cut down to 1/3, what's the new force? This is hitting on the inverse square law idea, the fact that the force has a dependency on 1 over r squared. So let's start with the double. If you double the distance, the inverse of 2 is 1/2. So we'll take 1/2 and we'll square it and we'll get 1/4. That means the new force you experience is 1/4 times the original force of 64. We get 16 newtons. As for the 1/3, same idea. The inverse, we're going to take the inverse and then square it. The inverse of 1/3 is 3. Now take 3, we square it, we get 9. Our new force, 9 times 64. 9 times 64 in the calculator, we get a new force of 576 newtons. And that's a wrap.